Today, you're going to get a concise yet thorough review of the AP Physics 1 curriculum. If you're not feeling super confident about your content knowledge, this is the boost you need. Over the past 18 years, I've been teaching physics and prepping people for the AP Physics 1 exam. And the thing about these cram sessions are, they either breeze through the topics too lightly or they don't actually follow the essentials posted by the College Board. So I made sure I followed the essentials posted by the College Board really tightly with some examples, explanations, and diagrams. Now, with that being said, if you want to take a deeper dive into some content and strategies, definitely take a look at a link in the description. It's got a ton of resources there to prep you for the test. All right, let's get into it. For Unit 1, we have kinematics. We have some basic terminology, scalar versus vector. Scalar, which is just purely a magnitude that's only positive. Some common examples are distance, speed, and time. For vectors, things with magnitude and direction, which would be depicted with a positive or negative sign for the direction, or also with an arrow. Common vectors are a delta x, displacement, velocity, and acceleration. The most basic kind of motion is constant velocity. So constant velocity is basically the same types of calculations as an average velocity calculation, because either you are actually going the same velocity the entire time, or an average velocity is just an approximation, which is saying that you're going about the certain velocity the entire time, with an acceleration of 0 meters per second squared for any of those different cases. So moving on, we have acceleration. With acceleration, you can either be speeding up, slowing down, or changing direction. Now, if you have a positive acceleration and a positive velocity, those are obviously working together. Therefore, you'd have an increasing velocity, or you have a negative acceleration with an already negative velocity. In that case, you'll also be increasing velocity, like something being dropped and being accelerated towards the ground by gravity. Now, if your value is decreasing, that means you might have a positive acceleration paired with a negative velocity, or a negative acceleration paired with a positive velocity. In that case, the force is working against the direction of the velocity, therefore decreasing it. And then lastly, like I said, we have change in direction here that we'll get more into with the circular motion section. Now, with the acceleration calculations, we have some kinematic formulas, and as long as you have 3 known variables, then you're able to solve for whatever you need to. Moving on to free fall motion, we have acceleration as either 9.8 or 10. Either one is acceptable with the calculations. I typically use 9.8, but you could use either one in the test. For ease of calculation, obviously you would use 10. You want to make sure you include the negative with your calculations, although the constant itself is listed as a positive. When you're putting it into those kinematic formulas, you definitely want to plug it in as a negative to depict the correct direction. Now, when something is rising up because its velocity is upwards and the acceleration is directed downwards, everything is going to be slowing down as it rises 100% of the time. It reaches an instantaneous velocity of 0 at the top. And then as it falls down, the velocity and acceleration are working together, so things will be speeding up the entire time. If things go back to their original height, then V0 and VF are going to be the same value, but just different signs, because one is going up and one's going down. Now, here's a little example of some different things that you might have to consider with a free fall type problem. And you have to be very careful with drawing pictures and including positive and negative signs. So for this one, we have 4 meters per second directed upwards. So that's going to be a positive 4 meters per second for our V0. We have a delta y of -2 because it's displaced downwards 2 from its original position. And then we have an acceleration of, again, -9.8 or -10 meters per second squared. For kinematics, you're definitely going to want to know your motion graphs pretty well. If you have anything that is a straight line of any sort, then it's going to be moving at a constant velocity. If it's curved, that means that the slope is changing. That means it is accelerating. If the slope is getting steeper, like this orange line or this purple one, then it's speeding up. If it's flattening out, like this red one or this gray one over here, that means it's slowing down. If it's headed in the downward direction, that just means negative direction. And if it's moving up on your graph, that just means positive direction. Now, anything that has any sort of slant on your velocity versus time graph, that means it's definitely accelerating because the velocity is changing. And if it's flat, that just means the velocity is constant. It only means it's at rest if it's directly on the x-axis at 0. Good rule of thumb is if it's moving away from 0, it's speeding up. If it's moving towards 0, it's slowing down. So the orange and the purple, which correspond to the orange and purple in the previous graph, those are both speeding up, moving away from 0 in the positive direction, and then this one is in the negative direction. For our accelerations, we only have uniform acceleration, so we either have things not speeding up or slowing down, which is right on 0, or they have a positive acceleration or a negative acceleration. Remember, that could mean speeding up or slowing down, depending on which direction you're going. So just a reminder of the previous page, if you have a positive velocity and then a positive acceleration, that would mean speeding up. If you have a positive velocity and a negative acceleration, it'd be slowing down. So basically, if you have the same sign for velocity and acceleration, your velocity is going to be increasing. If they're opposite signs, it's going to be decreasing. Some quick tips also is that the slope of the position versus time graph is going to tell you the velocities. The slope of the velocity versus time graph is going to tell you the acceleration. And little tricks you could use is finding the area between the curve and the x-axis is going to give you a delta x for our middle graph, and finding the area between your curve and the x-axis on your acceleration versus time graph is going to give you your delta v. Now, for our last kinematics topics, we have some frame of reference stuff. Just be aware that you might have to take some different frame of references when looking at stuff. For example, if a person is moving on a train moving 2 meters per second to the right, and the train itself is moving 20 meters per second to the right. It's 22 meters per second with respect to the ground. And then the same thing when you're talking about maybe two things that are moving, a person that's moving 2, and then a person that's moving 5. It's going to appear that person B is moving 3 meters per second with respect to person A. And if the person who's going at 5 is going the other direction, then they have a closing speed of 7 meters per second. So just a few things to consider for some different frames of reference or relative motion. When going to 2D motion, now we have some X and Y components. The X component is shown in green over here. The purple component is shown in purple, or the vertical component is shown in purple. The actual V naught itself is this orange vector right here. So a lot of times you will have to break up some components to figure out how fast it's traveling in the horizontal direction and the vertical direction. So some things to know about each of the axes is there are no forces acting in the horizontal direction. So you treat that as a constant velocity problem for this portion, and you only use V equals delta X over T. On the y side, it's definitely accelerating because of the force of gravity. So you're going to use all of your acceleration formulas, and each axis operates independently, as in if one has a really, really quick x velocity, that does not affect how it moves up and down. And because time is not a vector, it could be used in either one of the columns. Unit 2, we have forces and translational dynamics. So we have some types of forces that I won't get way too into, but we have the force of gravity that is typically considered to be straight down towards the center of the Earth. But obviously, when you're talking about some planetary bodies and things like that, that rule is going to change, but it's always towards the center of mass. And then we have the normal force, which is perpendicular. And it's a push that is typically from a surface. It also gives you your apparent weight. So a problem where you're maybe sitting on a roller coaster and your normal force is increasing or decreasing, it gives you the perceived weight that would be higher or lower based on the change in normal force. And then 3 other forces that we commonly see are applied force, force of static friction, and force of kinetic friction. Applied force is a pretty general push or pull by like a person or something of that sort. And then static and kinetic friction we'll talk about in more detail a little bit later. For Newton's third law, every force has an equal and opposite force, or they say all forces come in pairs that are equal in magnitude and opposite in direction. Now, just real quickly on that one, if you have a push to the right, then you'll have a push to the left. So it won't be an opposite force that one's a push and one's a pull. And I have another example over here that just says if you have a pull to the left, then you're going to have a pull to the right, equal in magnitude and opposite in direction. A real life example is a person applying a force on the ground of 500 newtons. So the ground is going to push up with the person with 500 newtons of force. If that exceeds their FG, then it's going to send them off the ground. Another case that's a bit of a trickier one, we have two blocks being pushed together because they're in contact. Anything's in contact sliding along like that might kind of trick people, but those normal forces are going to be equal in magnitude, opposite in direction. Even objects that aren't touching, like two things that have a force of gravity pulling towards each other, like maybe the sun and the earth. This is a terrible sun and a terrible earth, but hey, at least they're yellow and blue. And those two have an FG on them that are equal in magnitude, opposite in direction. It may not seem like it because the mass of the Earth is much less, so it's going to show you much more acceleration. Remember, forces don't cancel. Okay, so it's not like these two forces, because they're opposite in direction, they cancel because they're on different objects. For the Newton's first law, I summed it up in a sort of simple way that I like, which is something is just basically moving at a constant velocity or at rest unless a force acts on it. So some kind of external force causes some imbalance and then changes the thing's motion from constant velocity or rest. Okay, for example, if, say, for example, this is a ball that's swooping around in a circle, if you release it at part of its path, it's not going to continue to curve. It will actually continue to move in a straight line at a constant velocity, assuming that we don't care about the effects of gravity in that case. In our second case over here, we'll say that a person is maybe on a bus, and normally you'd be on a seat with a seatbelt, but we'll say there's not. So take a look at this black rectangle right here. If the person is trying to stay at rest, but then the bus moves forward, you see that they are moved to the back of the bus for the second part where it's a gray rectangle, where in reality, their body is actually trying to stay at rest and the bus itself is moving forward and they are staying at relatively the same position with respect to the ground. Next, we have Newton's second law, which I think is easily the most impactful of the three laws. The reason being is you can do a full force analysis of any situation and figure out its acceleration or lack thereof. So we have the sum of the forces or the net force equal to m times a. And when you break that down, you want to break it into two different axes, the x and the y, both set equal to m times a. We have an example over here where we draw the free body diagram. The free body diagram would be normal force up, Fg down, force of kinetic friction to the left, and tension on an angle. Now, when you actually get down into it to find the acceleration, you would break that Ft into its x and y components, or the x and then y, and then place those into the proper formula. So the way it would look for this one is ftx, we'll call that the positive, so ftx minus ffk equals ma for our f net x formula, and then for our f net y formula, we'll call up positive and down negative, so we'd say normal force plus fty minus fg equals m times a. In this case, in the vertical direction, the a would definitely be 0, and you would have some kind of non-zero value for f net, the acceleration for f net x. Two important scenarios that you're going to commonly bump into are things on ramps. In that case, you're going to use the same approach, except everything that's on the x-axis is actually parallel to the ramp, and everything on the y-axis is tilted, that is perpendicular to the ramp. Next, we have some pulleys. A couple of big tips for pulleys is that you have multiple masses connected to each other. Everything that flows along a certain direction is positive, as shown here. So actually to the right and down is positive, and then up and then to the left is negative. That is a bit tricky because that usually is not the case in most problems as far as sign convention goes. And then when you're finding the acceleration, you want to make sure you include both of the masses because they're typically being accelerated together because they're connected. Next, we have gravity, taking a look at that in a little bit more detail, where Fg is mg. G is either 9.8 or 10, typically considered 10 newtons per kilogram. And then that would be considered the weight. So if you want to break that down into more detail, especially talking about, say, a person and planet Earth, M1 would be a person, M2 would be Earth, and then r value would be the distance between the center of masses of both of those objects. G is our gravitational constant, and then Fg is still the same sort of thing, except this is just a much more complex version of it. Now, if you put this mg in over here, then both of the m's would cancel out. That would be the mass of the person in the case that I had told you. So then if you wanted to find the little g value, the acceleration due to gravity, which is basically our 9.8 meters per second squared, this would be the mass of the Earth. And then everything else would basically be the same from there. Next, we're taking a closer look into the two types of friction. As I mentioned we would earlier, we have mu, the coefficient of friction, which is the ratio of the force of friction that is opposing the push or pull divided by the normal force. I would say pretty much every case it is going to be less than 1. It is possible that is 1 or greater, but very, very unlikely. So I just consider it to be a number between 0 and 1 that is unitless, because if you're finding the ratio of two forces, the unit cancels out. So we have FFK, kinetic friction, of something that opposes a slide because of the irregularities in a surface. And then we have static friction, which is less than or equal to that mu Fn. So static friction is just going to push back as much as it needs to until it reaches kind of its maximum. So let's say, for example, a surface can push back with 5 newtons of force on a certain object. So if you pull with 2, it's going to counteract with 2. If you pull with 5, it's going to counteract with 5. If you pull with 8, then static friction is no longer acting, and there's a bit of a drop, and then it will change into kinetic friction. So then you'd have that 5 newtons trying to oppose it from static friction, and then it would lose the push against that 8 newtons of force, and then it would just be the Fa minus force of kinetic friction. On the same surface, the mu sub s, the coefficient of static friction, is going to be greater than mu sub k, the coefficient of kinetic friction. Also, we have some spring forces being introduced here. Springs are going to be something that are very commonly looked at as far as the oscillation unit. As far as the forces unit, it does pop up some. So we have negative k times delta x. There's a negative there because the spring force is always a restorative force. I'll tell you what I mean by that in a moment. The unit is a Newton over meters, how many newtons of force required to stretch it a meter. And then we have the delta x, that is the distance from its equilibrium position. So if its equilibrium or the natural resting position is right at that dotted line, if you pull it beyond that, the restorative force is going to pull it towards that equilibrium position. And then if you push it above that line, the spring force is going to push it down towards that equilibrium position. So the delta x is always the distance from where that dashed line would be. And then the force is always going to push or pull towards that equilibrium position. Lastly, one of the subtopics for forces is circular motion, which is actually a pretty big subtopic. Anything that's traveling around in a circle is always changing direction, therefore it's always accelerating. The velocity is tangent to the curve, and the acceleration is always centripetal, pointing towards the center of the circle. The centripetal force isn't a new force. It is just force of tension, kinetic friction, things of that nature. As long as it is center-seeking, pointing towards the center of the circle, it is considered a centripetal force. When you're taking a look at that, you're going to be using something along the lines of Newton's second law, but everything pointing towards the center of the circle is considered positive, like the radial inward position, and then everything pointing away from the center of the circle is considered negative. So very similar ideas to our net force equals ma, except some different ways of viewing positive and negative. Also, the net force does equal m times a, but a in circular motion is a v squared over r value. So the centripetal acceleration of v squared over r is then subbed in over here for the regular old linear acceleration, and then F net equals mv squared over r. Now, if you take a look at example of some orbit stuff over here, which is a pretty common circular idea. We do have that Fg that we talked about before as our net force for orbiting things. So it has g m1 m2 over r squared equal to mv squared over r, where an m is going to drop out. The m that drops out is the thing that's orbiting. So if you're talking about the moon orbiting the Earth, then the m1 and this m on that side would be the m of the moon, and the only thing that would matter is the m of the Earth, which means that anything that's orbiting at the same distance from the Earth would have the same sort of velocity. The period is always the exact inverse of the frequency, and oftentimes we use velocity equals 2 pi r over t, 2 pi r being the circumference, and then t being the period. So it's kind of just a different sort of distance over time calculation. Now let's take a look at one specific example. Let's say a person is going over a hill, which is a part of a circle. It's a semicircle, so it would be considered circular motion. We have normal force up and Fg down. The center of our invisible circle would be downward, so Fg is considered positive, and then normal force is up, so that would be considered negative, following the convention that I talked about over here in green. So um, in that case, there's also something else to consider, which would be the minimum velocity required to complete a loop, which is a square root of g times r. I showed you the setup and a little bit of the mathematics behind that. But long story short, square root of g over r is your minimum velocity at the top of a vertical loop. Energy, one of the really big topics as well. We have kinetic energy equal to 1/2 mv squared, which means it's always going to be a positive value. And then we have work, which is the energy that is being pushed in or out of a system. The force is going to be parallel times the distance, or you have Fd times the cosine of theta. We have the theorem where the sum of the work is equal to the change in kinetic energy. We'll talk about a little bit more of what that looks like with the full setup momentarily. We have the spring force, which is also known as UE, the the spring potential energy, which is often referred to as UE, the elastic potential energy. We have, which is 1/2 times k times delta x squared, and then we have gravitational potential energy, which is mg delta y, often known as mgh. We also have gravitational potential energy in terms of looking at planetary bodies and things of that nature, to where if r approaches infinity, then ug is 0 joules. So anything beyond that is going to end up being a negative value as you bring those two planetary bodies closer to one another. Now, conservation of energy is a huge, huge topic that you can apply in different cases, where work equals the change in energy. If you rearrange that a bit, it's mostly saying that the initial energy plus the work, which the work may be positive or negative, is going to equal the final energy, to show that the total amount of energy is constant. And then the work is going to show that if any energy is added or subtracted from the system from some kind of external force. Okay, so what that might look like oftentimes is that you would have an initial kinetic, gravitational, and elastic or spring force, and the same thing on the other side. And then if you have a scenario where you have some kind of external force acting, then you're going to have some positive or negative work value squeezed in there. Okay, like I said, that depends if the work is being added to the system or being subtracted to the system. The system is doing work on something else. Oftentimes, you can cross out some of these things, as if, like something starting from rest, you would cross out your K naught, or if something is falling back to ground level, then you could cross out a UGF. So you typically cross out some things, you expand the formulas, plug stuff in, and then solve for your unknown variable. We also have conservative versus non-conservative forces. That's just talking about stuff that's path dependent or independent. FG and FS are going to be ones that are independent, and then FF and F, air, like air resistance, those are path dependent, because if they take a longer path, then they push on that object longer, and that does matter. Now, our final thing is we have power. Power is the change in energy or work done over time. So it's how many joules of energy are released per second, which is known as the watt. We have some instantaneous power, which you can calculate by taking at the parallel force times the velocity, or FV times cosine of theta. So a classic lab scenario, demo, whatever you want to look at it as, is someone running up the stairs. If the same person runs up the same flight of stairs, they may do exactly the same amount of work, because their change in gravitational energy is the same from beginning to end in both of the cases. But if you do them in different amounts of time, the power is going to be greater for the 4-second run, because the work done per time is different. Fourth unit, we have linear momentum. Momentum equals mass times velocity. It's basically how hard is it to stop. So it's, some people call it inertia in motion. I don't really love that definition, but it does kind of work. We also have delta P, the change in momentum, which is impulse, which is known as J. That is the net force times delta T. Okay, and delta T is the time of impact. So a lot of times that might be a very, very small value. Also, you can find the impulse or change in momentum by mass times delta V, Vf minus V naught. One common rearrangement of the formula is F equals J over delta T. The force equals the impulse over the change in time, which is the impact time, as mentioned before. So if two things collide and come to rest, they might have the exact same impulse, but the force might be wildly different based on the impact time. If we have a large impact time, then we're going to have a small force. So if something hits something elastic or some kind of cushion where there's a large time of impact, the force is going to decrease. And then if there is a very short time of impact, like hitting concrete, then the force is going to rise dramatically. One graph that you might commonly see is a force versus time graph. And then because the product of force and time is the impulse or change in momentum, you can find the area underneath the curve to find the impulse, which oftentimes might be a little spike. So it'd be finding the area of a triangle. Now, for momentum, collisions is definitely the most significant idea underneath momentum, where momentum is conserved in all cases, assuming that there's no external forces acting on it. So, say for example, you have car 1 and car 2 that are colliding with each other. However much change in momentum one has, the other one has the same thing, opposite sign. So, if one thing gains, say, 20 kilogram meters per second of momentum, that's because the other one lost 20 kilogram meters per second. So, if you take a look at the MV of one and the M2 V2 of the other one combined, that total momentum is conserved. Therefore, all of the momenta afterwards is going to sum to be the same value. Now, taking a look at that, two important things to know are elastic and inelastic. Elastic, the kinetic energy is conserved. So if you use the same idea but change this to 1/2 mv squares for all of these, the kinetic energy is conserved, and these ones are always going to separate from each other. For inelastic, it is basically the same thing where momentum is conserved, but kinetic energy isn't conserved. So if you take the sum of the 1/2 mv squares before and after for both things, they will not be equal. If it says perfectly inelastic, then we know that we have two things that are hitting and combining with each other, and then they have the same velocity. But in all those cases, we do have some energy lost through heat or sound or some other means. Now, moving to torque and rotational dynamics, unit 5, you want to make sure you definitely have a strong foundation for kinematics so that when you slide to those rotational ideas, it's going to make it a lot smoother. So now we have, instead of our regular displacement, we have delta theta, which is the change in radians. A radian is the ratio between the s, which is the arc length of the circle, divided by the radius. Okay, so it's basically just a measurement of an angle, but it's not in degrees. Now, instead of velocity in meters per second, we have radians per second. Instead of meters per second squared, radians per second squared, all very similar. All times are in seconds. For force in newtons, we now have torque in a newton meter, which is basically just a force that causes a rotation or a twist. And then instead of just regular old mass in kilograms, we have the moment of inertia in a kilogram meter squared. We have a few different things to consider. Technically, counterclockwise is positive and clockwise is negative. Honestly, it doesn't really matter that much as long as you call different directions different signs. So if you called everything clockwise positive and then called everything counterclockwise negative, it would still work out to be a correct solution. We have three different formulas over here that you could potentially use. The bottom two are on the formula sheet. The top one is not. Just a way of converting some values if you need to from linear type values using some angular type values and vice versa. Next, we have torque. Torque is basically just a force causing something to rotate. So it's force times your lever arm times sine of theta equals torque. So if you have a fully perpendicular force, all of it is going into that rotation. If not, then sine theta is basically going to take care of that. If you see here, if you have something pulled on an angle with this blue vector here, you basically would just use the sine of theta so that you would then eventually get this purple vector, which would be the perpendicular portion that would make something twist or rotate. Now, taking a look at a common scenario that you might see is like a person on a beam with a cable attached to it. What you might see is the torque of the cable that's going in the counterclockwise direction. We call that positive. And then we have a torque from the person, which would be their mg, and then the distance from the pivot point, which would be right over here where that hinge would be, and then minus the torque of the actual beam itself. So you would take the point where the center of mass is, and then draw a vector there. And then you would use the lever arm from the hinge to that center of mass. And then if it were a case where something is at rest, then you would have 0 on the other end, which in this case, that would be very common. If you don't, then you would have the net torque equal to I times alpha. Again, here's a reminder that you would do counterclockwise minus clockwise. Okay, like I said, the vice versa version works as well. And then for I, you would have some form of mr squared with some different coefficients depending on if you're talking about like a ring or a disc or a rod. And then we have a couple other things to consider. The sum of the torques is the sum of the mr squared values. For example, if you have a merry-go-round with a person on it, the total torque would be the torque of the actual disc of the merry-go-round and the torque of the actual person from that that's included, and then their lever arm would be their distance from the axis of rotation. Also, any axis that is parallel through the center of mass, then I prime equals the moment of inertia from its center of mass, and then plus that mass times distance squared. That's typically not a really big idea, but it is one that's included in the framework for AP1. Now moving on to Unit 6, now we are for sure, again, connecting a lot of linear ideas to rotational ideas. So we have the rotational kinetic energy as 1/2 I omega squared, having to do with the moment of inertia and how quickly something is rotating as well. The work is torque times delta theta, again, very similar to the work formula we saw before, but just the rotational equivalence. And then same with a lot of these values too, is the angular momentum is conserved as long as there is no external torque added to it. A common example would be like the figure skater spinning, where their arms are inwards, then their I drops and their omega goes up, or their arms go out, which means their inertia rises, which means their omega value would drop down to keep that angular momentum conserved. If there's a change in angular momentum, it would be torque times that delta t. Remember that delta t is the time of impact. Now, if you're talking about a point particle specifically, which would be different than the figure skater type scenario, then L equals R mv times sine of theta. Now, when getting into rolling. Rolling is the same type of thing that we did before with conservation of energy, except now we have the total kinetic energy as the rotational kinetic energy, and the translational. Rotational is just how much energy it's used to basically spin itself, and then translational is the type of kinetic energy we talked about before that is dealing with its actual linear motion. So again, you would kind of line up all of your values and then sort of cross out things that you do that you don't need, and then leave the ones that you do to proceed with the calculation. So we have gravitational potential energy in this case. We have some rotational and translational kinetic, and then the same thing afterwards. As something starts rolling, if there is more rotational kinetic energy, then you're going to tend to have less translational, and vice versa. So in the classic ring versus disc, the ring is going to have more rotational kinetic energy. Therefore, it's going to have less translational. And then just the opposite for the disk. It's going to be less Kr and then more Kt, that therefore allowing the disk to quote unquote win because it has less inertia, less rotational, and then more kinetic in the translational direction. If it is slipping, those cases are when the static friction is changed to kinetic. And then it begins to slide because the static friction isn't catching it and then causing it to sort of like roll over. Next, we have satellites that are in circular and elliptical orbits. With something that is in a circular orbit, it maintains a constant radius. Therefore, the angular momentum, the total mechanical energy, the gravitational potential energy, and kinetic energy are all constant. With the ellipse, the radius or the distance from the center of the ellipse is not going to be consistent. And our gravitational potential energy and our kinetic are not constant. Now, as something gets stretched farther away from, we'll just say the sun, um, it's going to have a greater potential energy. Think about it like stretching a long spring. And then as that gravitational potential energy rises, that would mean the kinetic energy would have to drop. And then the same thing happens all the way around. Once it swoops around closer, it picks up kinetic energy, it gains velocity, and then that decrease in distance drops the gravitational potential energy at that point. Now with our UG, it is negative g m1 m2 over r squared, again, where r approaches infinity, then UG equals 0. So any distance between infinity and 0 is going to be a negative value, making that gravitational potential energy shrink. If something is trying to reach an escape velocity, that means a velocity where it is moving away from, we'll say, from a planet and then not getting pulled back down from its gravitational force. So we have our GMM over R, our gravitational potential energy, equal to our K. And then if that K is equal to or greater than that value, then the velocity is going to allow that object to escape. So there's a little bit of algebra, a little bit of rearranging, and we got the escape velocity equal to the square root of 2gm over R. And then the m that drops out is the thing that's moving away from that larger body. So say, for example, it's a rocket trying to escape from Earth. The mass of the rocket is going to be canceled out, and the mass of the Earth is going to be our remaining m. On to our seventh unit, which is oscillations. Again, we have the spring force of negative k delta x. Again, negative because it is a restorative force. We have an equilibrium position where the spring would naturally lie, and then the block would be at this dashed line. If it is stretched beyond that point, the spring is going to pull it back towards the equilibrium position. And if it's compressing the spring, it's going to push it back to the equilibrium position. Now, when it oscillates or goes under simple harmonic motion, it's going to sort of wiggle back and forth. The kinetic energy is going to rise and fall, and the spring potential energy is going to rise and fall as well. A pendulum has a very similar type of motion to where as it moves to its maximum distance, we call that a maximum amplitude. At that maximum amplitude, we have a maximum A, capital A for amplitude, lowercase a for acceleration, and then F for force. That restorative force is going to be the greatest when it is pulled furthest from the equilibrium position. At that point, the velocity is equal to 0 meters per second for an instant. Now, the restorative force that we're talking about with a pendulum is actually this component of Fg, because Fg isn't going to pull it straight towards the equilibrium position. It's just going to be a component of the Fg, this purple vector right over here. Now, there are a few different formulas that you can use. This one could be used for any kind of situation where the period is equal to 1 over f, so they're exact inverses of each other. For the actual period of a spring or a pendulum, you would use different formulas. The one for a spring would involve the mass and the spring constant, and then for a pendulum, it's going to involve the length of the pendulum and then the acceleration due to gravity. They look pretty similar, but they have some different variables involved. For the total mechanical energy, we have the potential energy plus the kinetic. If it's vertical, then we're talking about some gravitational potential and some elastic or spring type energy. Now, say, for example, you have a spring that's oscillating back and forth, which would be very similar to a pendulum oscillating back and forth. What we're going to have is two different graphs that are going to look pretty similar to each other. And if something is being pulled out to its maximum value, remember we have the greatest amount of restorative force, greatest amount of acceleration, and the lowest amount of velocity. So our velocity is going to start at 0. Now from there, the slope is going to be the greatest and slowly start to flatten out because that force is going to decrease. And then it's going to reach its maximum velocity at the equilibrium position. So you see the slope is very steep in the beginning, it gets continually more flat, and then flattens out as it reaches its maximum kinetic energy, and that's where it meets its EQ, its equilibrium position. And then from there, it's going to drop, and then its velocity is going to get smaller and smaller and smaller until it approaches zero again, because it's compressing the spring, and the spring is going to continually resist more and more until that velocity eventually reaches zero, and then it repeats the same cycle over and over. Now, for the potential energy, it's just the opposite. Because its initial position is stretched out to its greatest point, we have the most amount of potential energy there. And then same thing, just in the opposite direction. As the stretch gets less and less, which is that delta x, the amount of stretch from its equilibrium position, it's going to decrease until it eventually hits zero. Zero stretch is at its equilibrium position, and then it starts to compress the spring and then cause the potential energy to rise once again until it maxes out at its maximum compression point, which would be somewhere over here. And then again, it just sort of repeats the cycle over and over again. And then if you were to add these two energies together, you would have some certain amount of total energy that would remain constant, assuming that there's no external forces or heat created in the process. Now, moving on to Unit 8, our final unit of fluids, we have a density, which is mass over volume, which you can rearrange so mass equals the density times the volume. You got to be careful. My handwriting isn't amazing, but capital V is volume and lowercase v is velocity. So you want to make sure you don't get the two mixed up. And then we have pressure equal to the perpendicular force divided by the area. So if we have a little particle that's colliding into the side perpendicularly, then all of its forces applying pressure onto the container. If something is hitting it at an angle like this blue vector, then only this green vector is going to help apply that pressure to the container. So just the forces that are perpendicular. Now, when we have fluids that are flowing through pipes, the flow rate is the volume per time. We'll say this has a constant flow rate. So the same amount of volume is going through per time. So as you can imagine, if we have the same volume of, we'll say, water, then it would definitely have to move faster through here. So we would have a small area and a large velocity. For the big area, it's going to allow more water to go through, and then that velocity is going to naturally slow down. In the end, the product of A1 and V1 equals A2 times V2, which is known as the continuity equation. From there, we have the absolute pressure, which is kind of like the total pressure. We have a P naught. A P naught oftentimes might just be the atmospheric pressure of 101,325 pascals, or 1 atm, depends on what unit you're looking at. And then we have a gauge pressure. The gauge pressure is basically the pressure provided from the fluid. So in the case we're taking a look at here, we have rho g delta y. We have the density of the liquid. We have g, the acceleration due to gravity, and then we have delta y, basically like the height of fluid involved there. So if we were looking for the absolute pressure at the bottom of this container, we would just take the P naught, which would maybe just be the regular atmospheric pressure, plus the gauge pressure that we'd have to calculate, add those together, and then we have the absolute pressure, which, like I said before, is basically the total pressure. Now, when you're taking a look at fluids, buoyancy is going to be a big thing. That buoyant force is equal to rho Vg, capital V for the volume. As I said before, this rearranging of mass equaling out to rho v is something that you often use with fluids. So rho Vg is basically just the fluid version of mg. So the weight of the fluid displaced is equal to the buoyant force, which is Archimedes' principle. Here you're going to be using a lot of Newton's second law type stuff where you have a net force. And then in my case here, I said all the forces up were positive and all the forces down would be negative. So all the forces up would be the tension pulling up, the buoyant force for pushing it upward. Those are both positive. And then you have minus Fg, just our regular old force of gravity pulling it down. To close out fluids, we got Bernoulli's equation and Torricelli's theorem. Bernoulli's equation is basically a conservation of energy for fluids, where we have a certain amount of values in red over here for opening 1 over here, and then some certain values for opening 2. Now, a lot of times you will actually pair this continuity formula with it to plug in some areas and then probably solve for some kind of velocity that might plug into like a V2 or a V1 type of thing. Now, if there is some kind of difference between P1 and P2, you have to leave those. If they're just both maybe just regular 1 ATM, then those would cancel out. A lot of times what you would do is your lower point, you would just call that 0, and then probably cross out this rho gy2, and then have a rho gy1 value. But you can make your base at the lowest point of the problem and just call that 0, and then give the other one some kind of y value. So what you want to do typically is start out crossing out some values that you don't need, and then work with your numbers that you have from there. Lastly, we have Torricelli's theorem, where something is in a container such as this, and then there's a speed of a flux where the water is coming out at the other end, which acts just like if it were dropped from that particular height. So here's our height right here. If something were to fall 1 meter, like a ball being dropped 1 meter and have a specific velocity, the speed of a flux works just like that. So if you set mgh equal to 1/2 mv squared, rearrange it, then v equals square root of 2gh. So same sort of things with fluids. The speed that it's exiting at is the velocity of 2gh. Now, the thing that would make the problem a little more tricky is if your P1 and P2 aren't the same. Say if it's a sealed container where this pressure is maybe higher or lower, then you're going to actually have to use Bernoulli's equation and then plug in a P1 and P2. And then you'll definitely get to cancel out some values, but then you'd solve for a V2 in that case using Bernoulli's equation with a situation that looks similar to Torricelli's theorem. All right, that does it. The whole AP Physics curriculum in 44 minutes and 30 seconds. Make sure you take a look at the link in the description if you want some more strategies and some deeper review. Other than that, if you found some value in the video, please consider liking, commenting, or subscribing. Good luck on your exam.